Number 11's a lot like number 10. In fact, I used the same volumes for my weak base and for the same molarity for my strong acid, just so that as we look at the numbers, we can kind of jump to some conclusions or some answers a little bit faster without needing to think through the math as much, but also to see how even when the numbers are exactly the same, how it looks a little bit different for a base compared to an acid. So the initial pH of my base solution, it's a base, but it's a weak base. We're going to have a high pH. K equals x squared over molarity. I solve for my molarity, but because it's a base, we need to remember that x is equal to the concentration of the hydroxide ion. By using Kw, it allows me to find the concentration of hydrogen, and then that allows me to get to my pH, and it's a pH that makes sense based upon what we just said. It is a high value. This could all be in one step, could be in two steps, could be conceptual for multiple choice, but definitely being very comfortable with the idea of a high pH, not super high, not based upon just the molarity of the base, because it is a weak equilibrium. On part B, what's a little bit different on this one is molarity times volume times hydrogen, molarity times volume times hydroxide. That's all the same, but what we need to recognize here is that ammonia, NH3, doesn't really have any hydroxides in it. For these bases that are not like KOH, CaOH2, etc., we would need to think about, well, how many hydrogens can they accept? Sometimes that's given by the formula, like the carbonate ion, CO3 2 minus, that can accept 2 hydrogens. So that would have a 2 in the hydroxide section. And most other bases, unless there's like an obvious -2 or -3 charge, are just going to accept 1. So this math still works. You just need to account for that. Part C, very similar to what we did in our last part on number 10, the pH, at the equivalence point. Well, we know how many moles we have to begin with, molarity times volume. Well, that's how many moles of acid we would need to add. And we are at the equivalence point when we have reacted away all of our moles of base by adding that many moles of acid. Our limiting and excess are kind of changing places, or they're equivalent to one another. So that tells me how many moles of products I have made. I have made that many moles of water, and we often ignore the water. Technically, that's going to make the problem way harder if we account for the moles of water and its volume and all of that. So we get to ignore that in AP, but then that's the moles of salt. Same total volume. So the cue that you're going to be doing this in most AP problems, it will say, assume volumes are additive. That's your reminder. They don't have to say that though. So we have to remember that by the time we get to the equivalence point, we just have more liquid there in total. Moles over volumes, it's that same molarity we saw before. It is a similar equation here, but this is the conjugate acid of a weak base. It reacts with water to make hydrogen or hydronium ion. We need to change from our Kb to our Ka. We've got that. The Ka is x squared over the molarity. All of this is very similar. Our x, we get that as the hydrogen ion concentration. But the nice thing here, because this is a conjugate acid of a weak base, that means that the K we're looking at need to change it here, which I didn't, is a Ka. And that Ka means that we're already given the hydrogen ion concentration. We do the negative log of that. That gives me the pH without an extra step needed. And the other important thing with that is we have to be able to just estimate the pH. 7, above 7, below 7. Well, this one is below 7. The next part here, we've said it. The pH at the half equivalence point is equal to the pKa. But this is a base. Shouldn't it be different? No, it is still the pKa, because pH is about how much hydrogen ion you have, and pKa is about how much hydrogen ion you have. So we have a relatively small pKa. Our pKb, or our Kb is, a little bit bigger than our Ka, which is why it makes sense. Okay, this is 9.25. Part E is very important to be able to explain, understand, and think about in terms of that titration curve. So we started off high, and as you look at this and think about the problems, look at the notes. Think about the high start on the curve. Think about at what point it's kind of leveling off. Where does it drop off? And we did some of that math. So all of this is similar to what we've done before. And the other important thing here, we could even think about the pH. It doesn't ask about it yet, but we'll be doing that in the next sections and the next problems. So at the beginning, we have only ammonia. When we add enough acid, it starts turning into ammonium iodide and water. Eventually, the base runs out, and then we start to have some excess here. So at the very beginning, we have only ammonia. Here, we've only added a little bit of the acid. We are before the half equivalence point. So the little bit is important, but we know that we're not even halfway to being done. So we still have more of our base than its conjugate acid. 12.5 is important. We previously found out, and did in the previous problem as well, that 25 milliliters is needed to get to the equivalence point. That means 12.5 gets us to the half equivalence point. The half equivalence point is where I still have half of my base, but half of it has reacted. So half of my base exists, half of it has turned into its conjugate acid. The half equivalence point is where those two are equal to one another. That's why the Ka is equal to the pH as well. Right here, I am past the half equivalence point. I'm not all the way to the equivalence point, but it's important that, yes, I still have some base. Yes, my pH is still above 7. I still have that base. But I now have, in my equilibrium, I'm shifting more to the ion side. I have more of my, my ammonium than my ammonia. And that's because it's a one-way reaction. The stoichiometry shows that I've added almost enough base to, acid to react all the base away. In the previous part, we found out that 25 was the equivalence point. That means the ammonia is gone. Not only is the ammonia less than the ammonium, because this will be true for the rest, that ammonia equals 0 and the ammonium is equal to however many moles or whatever the molarity of our, based upon the reaction like we did previously. We can find the pH from it. We can do all of that. When I get to 30 milliliters of HI, I still have no ammonia. It has all turned into ammonium. But if I was being asked about the pH, which obviously I'm not, but if I were, the nice thing here is I don't even have to do an equilibrium, because now I do have none of this. I have some of that. Both of those are important, but I have an excess of strong. The pH is super low now because I have excess hydroiodic acid, which is a strong, totally ionized acid. So however many moles are excess determines my pH. That moles of excess, not total moles, but moles that after it all reacted with the ammonia, and the total volume now. So the 20 plus the 30. The nice thing with these, or the reason I did this conceptually, is you're not going to have to find the pH at all of these different places along the way. We have said that for AP questions. It gets into that equilibrium that we can't really solve for because we can't, we have to use the quadratic. But we should know what we have more of and be able to make pH estimates. So that's what we did here, and we're going to continue to do as we think about what is in solution.